How many atoms? Let's see how big atoms are.
Only 6?
9.
9?
Yeah.
Quantum mechanics.
Yeah.
That's the thing we are,
No one likes that.
You should be experts on quantum mechanics now. Okay. Right.
When is our assessment support this week?
Oh yeah, when do you want to do assessment support? Well, do we have class tomorrow?
No, we have 1 hour class in Wednesday.
Yeah.
Friday we have 2 hour class. I think Wednesday we have to.
Wednesday you have 1 and Friday you have 2.
Do you go Friday lesson? Like,
I have the maths exam on Friday, so
our timetable is horrible that day.
Yeah,
what's wrong with that day?
the Friday.
I think we have like 11 we have assessment support.
Yeah.
And then we have your class at 3.
Yeah, we have
Yeah.
3 hour and.
Oh, I see. You have a huge break.
Yep.
We'll see. I have the maths exam to do on Friday, so I'm very limited. I can't. Possibly. Like, what's happening on Thursday? What's your Thursday like?
Thursday is.
See, my Thursday is quite good because the maths exam is on Friday, so I shouldn't really have much to do on Thursday. So if you have free time on Thursday,
Absolutely.
ugh. I'll see. Leave it with me. Let's see. I'll have a look at my timetable when I go to the office. Okay, Kepler's Law. Write this down. Kepler's Law. Okay, got that? Now, Kepler was the person I was accidentally talking about last week before we actually did Kepler. Now we're doing Kepler. Okay, so Kepler has 3 laws, just like Newton. Except what you should know is Kepler was much before Newton, maybe about 100 years, or no, maybe not as much as 100 years, I'm not sure, before Newton. So these laws are before Newton's laws. And all of Kepler's laws have to do with planets in orbit. Earth, Moon, Mars, Sun, all these stuff. So Kepler's first law is a pretty easy law, actually. I mean, it's easy for us nowadays, but at the time it wasn't easy. Kepler's first law says, bodies in orbit of the Sun or other large masses move either in a circle or an ellipse. This is an ellipse shape. So, what Kepler's first law says is things will either orbit in a circle or an ellipse.
Egg type.
Egg type, yes. That's Kepler's first law. Yes, you do, because Kepler's law is not just for the Sun, although the Sun is what he was looking at when he arrived at this law. I'm sorry, those 4 words now are adding to your difficulty in life.
Elliptical?
Elliptical.
Elliptical.
Yeah, elliptical.
How many predict at that time then?
That's a great question, isn't it? I don't know. He must. Well, no. telescopes would have been good enough then. So it would have been possible to use trigonometry and telescopes to calculate the distance. So maybe what he did was something like he looked at the distance the Earth is from the Sun every week or every month, or the distance Mars is from the Sun, or something like that. And he noticed the distance got smaller, then it got bigger. So he maybe drew a picture and he could see, oh, it goes, you know. He could have done it, I imagine, by just after lots and lots and lots of observations of different planets and their distance from the Sun throughout the year. It would have been quite, you know, a big thing to do. Like, is that you can actually prove this by using Newton's law of gravity. The proof is a little bit difficult, but not impossible. It's university level proof. You can prove it. But of course, Kepler didn't have Newton's law. So he proved this by just observation. Yeah. He had enough data. Okay, next. Yep. The proof is too difficult for us. Kepler's second law. Now, I sometimes mix up the second and the third law. I think I have this the right way around. You got Google handy there? I don't want to mix up my second and my third law, because I did that last year. I think I fixed it. Just type in Keplers Second Law to Google. I mean, it's no big deal, but in the exam I don't want you confused, because the question might say, use Kepler's blank law. I want to make sure I get the number right. That's it. Yep, that's the one. Okay, Kepler's second law states that the area swept out by an orbiting body per unit time is constant. So, before I give you the formula, let me explain what that means. So, Kepler also noticed, here we go. Let's say you look at the orbit per month, okay? And forget about this one, we'll look at this one. So, here's January, it moves from here to here, okay? And then February, it moves from here to here. And then March, it moved from here to here. What Kepler noticed is that these areas, A1, A2, A3, these areas here, they're the same. That's what Kepler noticed. So the area swept out is a constant. It doesn't matter about the unit of time. You could do per day, per week, per month, per season. It's constant.
It's true?
Yes, it's true. It's true. So when it gets to here, so let's say it's whatever month this is, August or whatever, July or something. If this area is supposed to be the same as this area, then it means this distance here is bigger than this distance, which means it's moving faster here. So the speed is not constant. It moves faster as it gets closer to the Sun. This is Kepler's second law. In fact, you can state it as a formula. Mathematically, you can state it many different ways. Like, one way to state it is that the change in the area over the change in the time is a constant. But a more useful way to state it, I find, is that V1 R1 equals V2 R2. So if you were to look at the R1 and the V1 here, and look at the R2 and the V2, say here, that they're the same. That the radius multiplied by the speed will equal the radius multiplied by the speed at some other time. And what if it's moving in a circle? If it's moving in a circle, what's the relationship between R1 and R2?
R is same thing.
The same. So what's the relationship between V1 and V2? So if it's moving in a circle, the speed is constant, but you know this is circular motion. It's a constant speed in a circle.
In this way, the speed is not constant.
Exactly.
It changes.
It changes.
Oh
Oh,
yeah.
it's not circle.
This is, well, no, you could use this for a circle, but it gives you the useless result that V1 equals V2, that V is constant. But it's actually, elliptical is when you would need it.
So it goes constant and nearer to the sun it gets faster.
Yeah. Will I prove this? I used to prove it, but I don't see any point in proving it because it's definitely impossible to be on the exam.
Just second law is just area is always same.
Yeah.
That's it.
Yeah. Well, Kepler had to work very hard to figure that out.
Yeah.
See, Kepler used big data. He had lots and lots of data on the orbits.
The big data was really was big data.
Big data. Okay, got that? I think this is a very interesting result. Really, it's quite interesting. So it means as the Earth gets nearer to the Sun, it will be travelling faster. So remember in the homework we calculated the speed of the Earth around the Sun is whatever, 24 kilometers a second. Actually, that's just an average speed. At some parts it'll be going faster, and at some parts it'll be going slower than this. Okay, continue.
Oh, I got the reason.
Yeah,
The Earth
yeah.
wants to escape that location because it's so hot.
Yes, indeed.
Right?
Uh,
It's so hot.
not so right. Okay, Kepler's third law now. So Kepler's third law states that the time squared is proportional to the average radius cubed. That is, t squared is proportional to r cubed. As a formula, you can write it like this. Now, Kepler did not quite have this formula because, well, no, actually, you could have had this formula. Yeah. This is it as a formula. But what I mean is, when I said Kepler didn't quite have this formula, is for Kepler, he didn't know about G. So for Kepler, this 4 pi squared over G would have just been one constant in his formula, which he would have worked out from the data. So for Kepler, the 4 pi squared over G is a single constant. Although because of Newton, we know that's a 4 pi squared over G.
The M is from
The mass of whatever it is that's in the orbit.
It's not
Oh, sorry, the
big M.
the big M. Like in this case, it would be the mass of the sun. Yeah.
So like he knew everything but he didn't know that gravity exists.
Well, I mean,
Yeah, I think this is the hard thing in gravity.
everybody knew about gravity,
But like no one could say.
but nobody could say, like, you remember the quantum mechanics lecture I had? People didn't even understand that, like, people thought heavier things fell faster. So, like, you can know that there's a gravity, but you can then not understand it. So I don't know. I don't know if Kepler knew it was gravity that was making the Earth go around the Sun, or if he just thought there was some kind of. Well, you see, he didn't even know about force because Newton was the first one to use force. So he would have said there's some kind of thing that's keeping the Earth around the Sun, and he just worked out the relationships, but he didn't know what the reason necessarily was. It wasn't until Newton,
How could we calculate the average radius?
Well, like I was saying, you could look at the radius every month for 12 months and then divide by 12. Because the telescopes were quite good at the time. Quite good.
What is that one?
I think it's like 1600s. Like Newton would be late 1600s. I think Kepler maybe early 1600s. I'm not sure when Kepler was born. Can you Google actually when was Kepler born? We get a year on this. Okay, do we have this?
Yeah.
Now, this is one of the proofs on the exam that they ask you for. I think I said there's a couple of proofs that they ask in the exam. The first one is they could ask you for the proof of UVATS equations, but they've not done that yet. The other one, if you remember, is the exponential.
I equal I0
Yeah.
e to the power
Yeah.
minus 10 t over tau.
Taking the log of that
Right.
to get the formula for the relationship between the slope and the time constant. And the other proof is now this one. And this one actually, of the three proofs, UVATS they ask 0%, the log they ask 50% of the time, and this one here they ask 50% of the time when they ask for a proof. And they ask for a proof maybe 25% of the time. So I would expect 1 in 8 exams, about 1 in 8 exams at least, or maybe more actually, to ask for this proof. Okay, so let's have a look at the proof of this.
How could we do that? T.
This proof is, this proof is on the exam, and it's not in the formula book, this formula. Although it's quite useful to know this formula, it's not in the formula book. You should write that down, this is not in the formula book. And the reason it's not is because I think they ask you to prove it. That's the reason why. Right, let's go prove. Now the way we're going to prove it is not the way Kepler proved it, because we have Newton's law to help us. So let's look at the proof. Okay, so we'll say M. Right, so this is moving in a circle. Circular motion, so we can say F equals M omega squared R.
Yes.
But Newton said F equals GMM
Over R squared.
over R squared. So therefore, M omega squared R equals GMM over R squared. Cancel, cancel. And now, proof on exam. I'm not finished yet, I'm just make sure you know that this is on the exam. So then, omega squared equals GM over R cubed. Omega is 2 pi over T. So that means 4 pi squared over T squared equals GM over R cubed. So the result, yeah, T squared equals 4 pi squared over GM R cubed. That's Kepler's third law proven for you. Quite true. It's not that bad, is it? Let me think, yeah. Okay. Now, there's with a little telescope. Let me tell you why this formula is actually pretty amazing, if you really think about it. Here we are on Earth, and all we have is a telescope. Now, because we have the telescope and trigonometry, sine rule, cosine rule, we could work out our distance from the sun. We can know this. Agreed? A bit of trigonometry, we can know this. And of course, we obviously know the time it takes us to orbit the sun because we have the 4 seasons, 365 days. So, would you agree that it's quite easy to know these things
Yeah.
with a telescope? But by knowing these two things, we can know something quite amazing like the mass of the sun. Now, really think about that. With just a telescope, you can work out something like the mass of the sun. Not only that, let's say we were on Earth and we were looking at something like, say, Mars. And here's Mars and here's a moon of Mars. Okay? Using our telescope, could we know the distance between the moon and Mars? Yes, we could. And if we look through our telescope, could we know the time it takes for the moon to orbit Mars? We could. So if we know the radius between Mars's moon and Mars, and the time it takes Mars's moon to orbit Mars, then we could work out the mass of Mars. And in this way we can work out the mass of all the planets, since most planets have a moon to orbit it. Even Pluto, which is not really a planet, has a moon. So this, I think to me, this is the most powerful thing about Kepler's third law, is it lets you work out the mass of planets by simply observing the time and the radius of its moon. Yeah. Okay, continue. Right, some definitions before we look at examples. A geostationary orbit or a parking orbit. Now maybe somebody knows what this means actually, or could work it out.
Geo plus stationary.
Yeah. Also called parking orbit.
Parking is track something?
Yeah. Does anybody know this? No?
It's a special orbit.
Yeah, it's a special orbit. What's special about it? So, huh? Yeah, but kinda. But it has to be moving because it's an orbit, but not moving.
No.
Its orbit around the Earth is 1 day. So, for example, let's think about it like this. Here is the Earth, and of course here we are at 0, 0, 0, 0, and then 12 hours later, here we are, and then 24 hours we're back here. If there was a satellite above us, orbiting us, if it had a time of 24 hours, then it would look like it wasn't moving, because it would always look like it's above us. So it appears fixed in the sky, really is just moving with us around the Earth. So this is a parking orbit. Which satellites use this one? Well, TV and GPS. I mean, think about it. If you have a house here, let's say you live here, and you have your satellite here on top of the house, you really want this to be fixed, because you don't want this to move. You want it just to look at one spot in the sky to get the signal. I think GPS is the same. It's fixed in the sky, I think. So this is a geostationary orbit or parking orbit.
It moves, we have different channels everywhere.
Huh?
If it moves, we have like different.
Yes. Yeah. That the sort of Indian satellite would come into your view and then leave your view and everything. Yeah.
Like sharing culture.
Yes. Yeah, but the problem is you would have to move your satellite on your house throughout the day to keep repositioning it. Okay, you got that? Yep. Continue.
Yep.
Bruce? Yep. Okay. A small satellite in a parking orbit around the Earth, how far is it from the surface of the Earth? From the surface of the Earth. Right, so we could use Kepler's Third Law here, which I... T squared equals 4 pi squared, yeah, over gm or cubed. And what am I looking for here? I'm looking for or. How far is it from the Earth? So the or would be g t squared over 4 pi squared cube root. Right, so let's calculate the distance here. So cube root, so I don't forget to give it back to you, thank you. What did I say the mass of the Earth is, please?
5.97 by 10 squared.
24, isn't it?
24, yeah.
And the T is 24 hours, which is 24 times 3600. And then you have 4 pi squared. Now, I want the distance from the surface of the Earth.
Minus.
So I have to minus from my answer 6371000.
That's
Because I don't want the distance here, I want it from the centre. This will be a pretty big number. These parking orbits are very high orbits. I'll put in kilometres. 35,864 kilometres from the surface of the Earth. So these parking orbits are really big orbits compared to the Earth. Really big orbits.
Can we go back to the question?
Yeah.
What is T?
24 hours. Because I said a satellite's in the parking orbit.
We need it in seconds.
Yeah. Continue? No? What's wrong, Wade? Continue?
Yeah.
Okay. So, the planet Mars is observed to be 228 million kilometers from the Sun. One Mars year, so I've got an apostrophe there, one Mars year is actually 687 Earth days. So if you were living on Mars in 2025, for 1 year would actually be 687 Earth days. And I think 1 day on Mars is about the same as 1 day on Earth, or maybe it's a difference of an hour. Anyway, firstly, calculate the mass of the Sun. Okay, so we use Kepler again, although we want to use Kepler slightly differently. This time I want the M. So the M would be 4 pi squared or cubed over gt squared. Four pi squared times or cubed over g squared, g times t squared. Now, what did I say it was? 687, wasn't it? So that's 687 times 24 times 3600. 687 Earth days is the time, the orbit time for Mars, and then the distance Mars is from the Sun is 228. 1, 2, 3, 1, 2, 3, 1, 2, 3.
Really? 10 to the
6 kilometers is 10 to the 3, so it's 10 to the 9. We know the answer. The mass of the Sun is something like 1.99 10 to the something big. So yeah, 30 is it, or something like this? There we go. Very good. 1.99 10 to the 30. Ah,
680.
687 days times 24 hours times 60 minutes times 60 seconds. Ah, yeah. Yeah. Is this okay? Next now. What is the V? Okay, well the V, that's fine. That's V equals omega r, isn't it?
Yeah.
Which is 2 pi over T r. Now 2 pi T.
Why there's T is over?
It's over, sorry. Yeah. Oh, okay, let's just start again. 2 pi
R.
r
2 to 8.
over
6, 8, 7, 3, 4, 5, 6, 7.
okay, so again it should be pretty big. 24.1 kilometers per second. Yeah? Now, we have to be careful because the orbit is not a circle, it's kind of an ellipse. So, I mean, we're imagining it like it's a circle around the sun, but it's actually an ellipse. So, for some part of its journey, it will actually be the 228 million kilometers away. But for other parts, it will be less, and for other parts, it will be more. And for some parts of its journey, it will be going 24.1 kilometers per second. This is for the radius will be less, and the radius will be. Where's my? There it is. Oh, sorry, not this out. Radius will be more, and then for some parts, the velocity will be more if it's closer, and for some parts the velocity will be less. Now, for the last part here, I'd say the orbit of Mars is not a circle, it's actually an ellipse. At the nearest to the Sun, it's 207 instead of 228. What is its velocity here? Okay, so we imagine here when it's nearest, it's 207 million kilometers. That's the R2, and I want to know what the V2 is. So, Kepler's second law says V1 times 10 to the 3 kilometers per second. V1 R1 equals V2, which is what I want, times R2, which is 207. So that's, we can cancel that with that. What else?
Yeah.
Oh, that's all we can cancel, isn't it? So I get V2 will be 228 over 207 times 24.1 times 10 to the 3. So it will be going 26.5.
No.
No?
We have like 10 to the
No, because I already, in my head, I just changed this into this. Yeah. 26.5 kilometers per second. You know, that's quite a bit different. It's an extra 2 kilometers per second faster, about. A bit more, actually. Yes.
Are there planets that fall in the system?
I think the moons or orbit around the Earth is actually pretty circular. And I think perhaps Mercury and Venus, the two nearest planets, are pretty circular. But then, once you get past Venus, like Earth, Mars, Jupiter, Saturn, it just is more elliptical. Okay. Shamsa, you have this? Yeah. And do we all have this? Yeah. Okay. So, let's see. Just one question for homework, if you can. Just one question for homework.
Looks like one.
Yeah.
That's to do with Mars.
And Kepler was born on 1571.
1571, so it would have been around about 1600 when he made his laws, I would have thought. He would have been about 29 perhaps. Oh, yeah.
Where is he from?
He was a German.
German?
German, yes. Yeah. 1571. Okay, can you take a picture of this if you like? And we have about 5 minutes left if you want to get a start on it. Oh, there you go. One day on Mars is 24 hours and 40 minutes. Got that? I can close this? Okay, so if you try these for 5 minutes then.
Two moons. The moon.